my talk will be about design for experiments and surrogate model extraction for antenna design. The points I'll be covering, I'll start with the design problem, and then I'll explain how a surrogate model might help in the design approach, how to create a surrogate model, and the advantages and disadvantages, and finally the conclusion and future work. Now, if you're not familiar with the terms design of experiments and surrogate model, then you would ask, what do they mean? I'm not going to explain it straight away. I'm rather going to start with a simple design problem, and in the course of the talk, I'm trying to explain those two concepts and how they might help. So a really simple design problem. We need to design a pyramidal horn with 20 dBi gain at 3 gigahertz. We could use a conventional design method using references, textbooks, and so on to calculate the design, then create the model in CST, and then we have to simulate this to verify our results. Or this can take minutes to hours or even longer. Or I would advise using Electromagnetic. Do a quick design, export to CST, and you'll get the same results within minutes. Now, if we make the design a bit more complicated or more specific, let's say we want an explicit E-plane beam width or an H-plane beam width, 15 degrees, 75 degrees respectively, and we also want to maximize the aperture efficiency, then Electromagnetic might not be able to help you exactly. So Electromagnetic lives outside of Electromagnetic's limits, and so what can you do? You can design for the closest possible objectives, which is in this case 15 degrees and 60 degrees, and you've got no option to maximize the efficiency. So the next step would be then to do the design as close as possible, export to CST, and then do an optimization. Now this might not necessarily give you what you want. You might be closer, or you could go the conventional method again. I doubt whether there's an explicit design for these objectives out in the literature. You'd also have to optimize, get the same results, and this might also take an hour or more, maybe days. So the alternative approach is to maybe use a surrogate model. So what is a surrogate model? The Wikipedia definition says a surrogate model is an engineering method used when an outcome of interest cannot be easily measured or computed. So an approximate mathematical model of the outcome is used instead. So in other words, we would like to create a mathematical approximation of the horn that can be used to predict its performance. So looking at our previous example, where you use Magus or references to get a specific design, which might take an hour or more, we could instead have a surrogate model. So this is a mathematical representation, and then optimize this surrogate model, which should be very quick, less than a minute. Then we do one simulation as a verification CST, and then the question is, but how well does this perform? So next, I would explain how to create a surrogate model, and then in the end, we will compare the results. Before we continue, I would just like to have a terminology alert. So I talk about KPIs in some cases. So in this case, it could be the directivity, the beam width, the side lobe levels of your antenna's performance. In Magus, we call this objectives. However, on the 3D experience platform, they're called outputs. The physical or geometric values of which describes your antenna, in this case, the flare length, aperture height, aperture width, are called parameters in Electromagnetic, but on the 3D experience platform, they're called inputs. I'll try to stay consistent from now on using inputs and outputs, but in case I change these terms, don't be confused. So next is the whole workflow of how to create a surrogate model. There are 6 steps, which I'll go through separately. It's to create a model, in this case, just your simulation model, then how to set up and run your design of experiments. Next, you have to review and edit your results. The fourth step is to create an approximation, which will be used as your surrogate model. You need to check the accuracy of your approximation. And after that step, you might have to go back to step 2 or 3, or maybe both. And lastly, how to use your surrogate model. So the first step is to create your simulation model. It's quite simple. You use Magus, I would advise, or references to create a custom model. In CST, the model should be parameterized, which is quite important. And your KPIs, or the outputs you're interested in, should be defined as 0D results. For more complicated results, Python scripts can be used. The next step is to set up and to run the design of experiments. So what is a design of experiments? I'm showing two quotes from the internet. I like the bottom one more, from jmp.com. Design of experiments is a systematic, efficient method that enables scientists and engineers to study the relationship between multiple input variables and key output variables. And the last sentence is quite, I think, puts it all together. It's a structured approach for collecting data and making discoveries. I've used the optimization process controller on the 3D Experience platform to create my design of experiments. It only has 2 blocks. The top one is the design of experiments adapter, where you define your design of experiments parameters, which will then control your CST model, which will be run after each variation. Some of the parameters that needs to be set up in the design of the DoE adapter is what type of a DoE method will be used. The DoE method determines how the values or the inputs will be sampled. So I've got 2 images. The one on the left is both just represent 2 variables for illustrative purposes. So if you do a parameter sweep in CST, you will basically do a uniform sampling. But it's better to use something like a Latin hypercube technique, which is a class of experimental designs that efficiently samples the space. Next, we need to define the ranges and the number of variations. 2 large ranges might require more samples and include different modes of operation in your model, which in turn might make an accurate approximation difficult. 2 small ranges might not capture all the changes in performance characteristics of interest. The number of variations also depend on the number of inputs and outputs, as well as the input ranges. Then, when the DoE is run, basically that's supposed to be a GIF, which is not working. Oh, there it goes. Okay. So basically, it goes through all the variations where the 3 parameters are varied, and after each one, a CST simulation is run. The outputs are captured and saved, which will then be used to review the data in the next step. The next step would be to review and edit the data. Here I've used Results Analytics, also on their 3D Experience platform, and they've got various visualization options. I'm only going to show a couple of them, as there are too many to go through all of them. In this case, we look at the correlation table. So the darker the color, the stronger the correlation between the inputs and outputs. Blue indicates direct proportionality, while red indicates inverse proportionality. In this case, aperture height has a strong influence on the beam width in the phi equals 90 plane, which is the E plane, and the red indicates they are inversely proportional. Those of you who are familiar with horn antennas would know this means an increase in aperture height will result in a decrease in the E plane beam width. Then there are also the 2D scatter plots. So looking at the scatter plot on the left-hand side with the 3 dB beam widths, we can see that there are actually no beam widths more than 70 degrees, although the requirement in our second example wanted a beam width of higher than 75 degrees. So why is that? We can use these scatter plots to try and determine whether we can figure this out. So just have to rerun the. Yeah. So you select all the points close to 70 degrees. When you select these points, all the same data points will be highlighted in all other charts. Now we can see all of them are for small aperture height, the smallest in our data set, except for 2. And if you hover over them, we will see that these 2 are just cases with a really short flare length. So perhaps our 75-degree requirement wasn't achievable in the first place. There's another way to look at the data, and that's the parallel coordinates chart. Here, all the inputs and outputs are on parallel bars, and each where all of the variations are connected. So again, we can, let's just start that GIF again. So what you can do is, on the bar, you can create a slider. Then it will highlight all the connected data point values. So we take the highest beam width. We can add a second bar, and we highlight those 2 outliers. And again, we can see they have a low flare length, small flare length, and very low efficiency. We can drag that bar down to the bottom where we know all the other cases are. And again, they're highlighted. And now we can see they all have fairly high efficiency. And we can add another, and the flare length vary from almost across the range. So you can add a third slider and move that up and down and see how the efficiency changes as we move it up and down. And as we would expect, for higher flare lengths, longer flare lengths, the efficiency is the highest. Now that we've explored our results, we can create an approximation. This approximation will then be used as a surrogate model. There are various approximations to choose from. I'm not an expert in all of them, so I stick to the radial basis function one, as it gave me the best and consistent results. After the approximation has been created, we need to check the accuracy. This was done in the Results Analytics app, specifically the guided analytics part. Previous results have shown it was also in Results Analytics, but the Visual Analytics section of it. So here we're just looking at the E-plane beam width, and there are various measures to decide to see how accurate your approximation is. The R-squared adjusted, root mean square error, it shows residuals, and so forth. This isn't the best approximation, so you can exclude outliers to try and improve the approximation, which I've done. So this is again the E-plane beam width with a better approximation. It still shows that the root mean square error, it might be a bit high, but I found that for my example, this worked fairly well. So if we look at the other approximations for the other outputs, the H-plane beam width, also satisfactory, as is the efficiency and the broadside directivity. The approximations for side load level is not really satisfactory, so maybe it shouldn't be used in an optimization, or it shouldn't be trusted. Lastly, we can use our surrogate model for designing. Again, process setup and process composer. We've got 3 blocks. The first is the optimization adapter. Here, the design requirements are specified as targets for the output objectives of the approximation. Bounds can also be placed, or targets placed on the inputs for the antenna, and this can be useful when there are size constraints. The surrogate model will then be used, or the RBF approximation we created in the previous steps will then be used as our surrogate model to find the optimal input values for our targets. Once the optimization is finished, the input values are sent to the CSD Studio Suite model, and the model is simulated to verify the prediction from the surrogate model. So to compare from our second design example, the surrogate model predicts values. Then we verify that with the CSD simulation. And you can see that the predictions by the surrogate model and what we actually achieve with our CSD simulation are almost identical. Even the side lobe levels, which I said didn't have a good approximation, was also well predicted by the surrogate model. And the surrogate model, the optimization ran within less than a minute. Our verification simulation was just 2 minutes. Now, if you compare that to our optimization in Studio Suite, that took more than an hour. So at this point, this looks like a really good alternative. However, there's one thing I haven't mentioned yet, and that's the actual time for the whole setup. So we're now creating a model using Magus, and then to exporting to CSD takes mere minutes. I've shown in the previous slide that using the circuit model for design also takes a few minutes. However, the setup time, the review of the data, checking the accuracy and going through the process until you've got an accurate approximation can take hours, even days. So the question is this really worth it? And for that, we look at the advantages and disadvantages. So the disadvantages is the initial setup time from DoE to an approximation is quite high. It remains an approximation, so you always need to verify it in the end. And you've got the curse of dimensionality, which means if you have too many input and output parameters, you may not even be able to get an accurate approximation. The advantages is if you've spent the time to set this up and you have an accurate surrogate model, it's repeatable and quick. And if your antenna requires repeatable designs for different requirements, then the cumulative time for this conventional optimization can easily exceed the setup time for a surrogate model. Even without using a surrogate model, just visualizing the DoE data gives invaluable insight into the interaction between your inputs and outputs. So to conclude, using DoE and surrogate modeling has definite advantages. The surrogate model can reduce overall time when doing repeatable designs, and visualizing relationships between inputs and outputs provides valuable insight into your design. As I've said, one of the disadvantages are that an approximation might not always be we might not be able to make an approximation due to high number of input parameters and output parameters. And there we started looking and investigating into using deep neural networks as surrogate models. The advantage here is that it's capable of handling way more parameters, and the antenna we've been looking in currently has 19 parameters, and the 2 images below shows our best prediction and our worst prediction. And I think in general, it looks very promising, and I think it is an exciting topic to further investigate. Thank you.